So he considered in 1709 the following actuarial insurance problem. He wanted to calculate the mean duration of life of the last survivor, extreme, among among n men of equal age who all die within t years. He reduced this question to the following. So this is now my t years, 0 to t, and I have these random points on this line. And so n points lie at random on a straight line of length t. Calculate the mean of the largest distance from the origin. It's just an extreme value problem. Now, of course, this is probability 101. But it was not probability 101 in those days. So that's, I think, for me, it's one of the first real nice problems where extreme value theory entered. Of course, it would not make Nicolaus Bernoulli the father of extreme value theory if we want to find a father or a mother. But if I were to ask you, I think most of you would say Poisson. The theorem of rare events, the weak convergence of a sequence of binomial random variables when Pn goes to nPn goes to lambda, which of course is very important extreme value theory. That's where the Poisson approximation enters extreme value theory. Well, as so often, the theorem of Poisson was already in the work of Coates and de Moivre. But anyhow, so he somehow is quoted or very often seen as a star, but it's not my first take home. My first take home is the next person. This is Ladislaus von Bortkiewicz. And normally, if I show this person, I first ask the name and then say, anybody knows him? Does anybody know Nicolaus von Bortkiewicz? Well, you see, there's a first take home, all right? Remember his name. Nicolaus von Bortkiewicz, in the actuarial mathematics, is famous for known for one of the most famous data sets. You know, like in multivariate analysis, the standard data set is Fisher-Iris data. And every field has its famous data sets. That's for discrimination and discriminant analysis. This is the first famous data set. This is the number of soldiers killed in a year in part of the Prussian army by kicks of horses. And that he modeled by using the Poisson. So that's von Bortkiewicz. But much more important, he wrote this book, Das Gesetz des kleinen Zahlen. Sorry? Yeah. No, it's a very nice data set. It's a standard data set to introduce. Of course, later we had the physicists with Rutherford and so on very nice Poisson. But this was a very nice data set. Yeah. There's a whole story behind that, but I will not tell it here. Perhaps with a glass of wine. But anyhow, so he wrote this book, The Law of Small Numbers. And the law of small numbers is like the laws of rare events. So he really, I think, should be viewed, if at all, as I think a founding father of the field of really modeling of extremes. And then, of course, we had numerous developments after that. Okay, so especially the early century, 20th century, and we saw many of the names before. I agreed with one of the speakers that we should have Khinchin here. I mean, the theorem was here at this part of the blackboard. It's now gone, but it was there. The name of the theorem was not mentioned. It was about weak convergence of two sequences, both affinely transformed and going to the same limit, going to a weak limit. Then the sequences have to be if you have the same sequence of random variables which are the different affine transformations convert to different limits, then the sequences have to be linked and the limits have to be of the same type, location scale. That's the famous convergence to type theorem. And the convergence to type theorem, which is Khinchin's, is responsible for discovering, let's say, the Levi stable distributions in the general central limit theorem, and is responsible for finding the Frese, Babel, and Gumbel distributions in extreme value theory. Because using Khinchin's theorem and half a page of just easy calculations, you find functional equations for these limits, you solve them, and then you get the Fisher-Tippett theorem for extremes, and of course if you go to the central limit theorem, you get the alpha stable Levy laws. Okay, so that's very, very fundamental. And there are many, many general formulations. So Khinchin, I totally agree with the speaker, that's one of the real fundamental theorems underlying not just extreme value theory, but weak convergence in probability. And then of course we have various mathematical developments. Richard von Mises, I think he did quite a lot of interesting examples, and mainly Gnedenko. I think Gnedenko should be quoted also, I think. So it's a nice Soviet sandwich with Kinchin and Gnedenko. That was in the Second World War, 1943, Gnedenko. A wonderful textbook summary, which I can really still, especially for physicists, engineers, really tell you should read it. It's in Dover Publications, republished, is Gumbel. And Gumbel, he somehow summarized the knowledge of extreme value theory in the mid of the last century. You see, 1954 is in the National Bureau of Standards. And of course, now we really have the field, statistical theory of extreme values, and some practical applications. A wonderful book. I think it's still not beaten today, I think, with respect to real understanding of the issues of the subject. We have added a lot of technicalities, but not always a lot of extra thinking. I think it's a wonderful book. And then, of course, the later 20th centuries, this is a very biased choice, but it's not so biased. I think Lawrence de Haan should be one of the absolute fathers of modern extreme value theory on the mathematics. Sid Resnick from Cornell, Richard Smith, previously Cambridge for a short time, and Ross Ledbetter. I'll come back to some of them later on. And of course, there are many more people. But I think if I had to choose 4 people, these are the 4, okay, that have developed what you and we are currently using. So all the theorems I've seen mentioned here, all the techniques I've seen here these days, will very strongly be based on work of these 4 authors. And now, of course, we had an enormous explosion. Okay, now this is a random collection. It's not totally random, because there are 2 of my books in there. But in 1997, we wrote a book on the modeling of extreme events for insurance and finance. And then recently, I wrote a book with Guus Balkema on high-risk scenarios and extremes, a geometric approach. This is the European Mathematical Society. This is very mathematical, but I think really interesting. I would not be able to speak about multivariate extremes, but I think that's, for me, beautiful mathematical theory, even in infinite-dimensional spaces among processes. But you see, there's a whole plethora of books available now in all fields. And of course, there's a famous journal now, the journal Extremes. And I think it's now a highly developed field, and basically all the sciences now use these things. And of course, the question of extremes, as we've seen at this conference, are omnipresent everywhere. Now, here is take home 2. I said my work is very much related to quantitative risk management, especially application to insurance and finance. Although I also work with environmentalists together. We have a joint collaboration with NCAR, International Center for Atmospheric Research in Boulder, Colorado, with Greg Holland and his colleagues. But mostly I go more to finance and insurance. And something I've learned, but I've learned this in every field of applications, and I've learned this here, is that practice is too often frequency-oriented rather than severity-oriented. We often talk about, let's say, every so often, or a return period, 1 in so many years events. In finance, you call this value at risk. That's how it's called if you go to the regulators. That's why I mentioned Basel here, because that's where the regulators have their head office in the Bank of International Settlements. That's calculating the physical dike heights of banks are based on a frequency measure, not on a severity measure. The severity measure is much more important. It's the what-if question. What is the height, the expected height of a tsunami off the coast of northern Japan if an earthquake, a 1 in 1,000-year event earthquake, which was a 9.0 earthquake off the coast of Japan, happens? It was 14 meters, and not the 4 or 5 meters that was used for constructing some of the latches of the atomic power constructions there. So the what if, the loss size given the occurrence of a rare event. Again, in finance, this is very important. This is the expected shortfall. Conditional expectation of a high loss. I take this 1 in 100 loss, say. What is the expected loss? That's the question that we should be interested in. And by the way, this can be a triviality in mathematics, but it's absolute a change in attitude out there. And I could now give a whole talk or course on the current discussions in financial regulation for banks. Because now, exactly now, in Basel and internationally, they discuss moving from this risk measure, a 1 in 100 event, to this measure, the expected loss given you exceed the 1 in 100 event for calculating financial could call dikes, financial reserves for banks, solvency for banks and insurance companies. So it's absolutely, and EVT is exactly answering this question. I will present the EVT that most of you have used these days. So this is take home 2, moving from frequency to severity. And of course the reinsurance world, this morning we had a talk where reinsurance at least was mentioned, of course is very well aware of that. In the reinsurance world there's something called XL treaties, excess of loss treaties. So a reinsurer very often has treaties with an attachment point, 2 attachment points, and you cover the loss, the underlying loss of the primary insurer in between these limits. And these limits are determined so exactly like a frequency measure. It's that particular level U, which is a 1 in 250, for instance a year event. If you were to attach a reinsurance treaty in northern Italy, this would be typically 1 in 250, 1 in 500 year events. That's what you attach typically the reinsurance treaty, and it may then go up a layer, couple of million, whatever, above that. That's sort of typical reinsurance. And the first reinsurer, he will cover that layer. The primary insurer keeps everything below that. And of course there's a pricing for that. And so the reinsurer is very much interested in this distribution function. Namely, F super UX is the probability given, and now you see this is a what-if statement, given I have a loss above this high attachment point, this 100 and 250 year event, what is the distribution of the excess? In insurance, in finance you would look at this. In reinsurance at this. Because you take that part of the layer, you reinsure whatever is above you. Okay, so that's just a standard in insurance. So this is called the excess of loss XL. What are good models for that? And this, of course, we have used already a couple of times this week. This is the famous Pickens-Balkenende-Hahn theorem. And an American reinsurance actuary, he once told me, for him this is by far the most important theorem ever to come out of mathematics for reinsurance. And you see immediately why. Somebody this week asked the question, what is a GPD? So let me now give you the basic theorem behind the GPD. This is by Pickens-Balkenende-Hahn, independently Balkenende-Hahn in 74, 75, and Pickens. You see, here's my FU. So I'm interested, is there a canonical model out there for this high excess distribution? This high excess distribution for large U. And let me always, when U moves up, let me say U moves to infinity. So I'm interested, I've got the reinsurance data here, or insurance data, whatever data, independent of the field for the moment. I'm interested in a high threshold, so U goes to infinity at some point, mathematically as a function of the sample size, very precisely. And I'm interested in, are there models for these yellow peaks above high thresholds? And yes, there are. And this is the GPD, the generalized Pareto. This is a very famous theorem. And here is its full mathematical detail, because that's rarely stated in more applied. So whenever you read XF, read it for infinity. The size you had before, that's psi positive. I can have psi 0, the Gumbel. I can have psi negative, that would be then the Weibull with an upper bound. But let's take the Frechet class. So this theorem gives me a limit for U tending to infinity. Supremum, this you get for free, because you're talking about convergence of distribution functions. For this sought after conditional distribution function FU, and here is the limit. The limit is a 2-parameter family, G and beta. Of course, the beta depends on the U here, but it's a 2-parameter family, and this is the GPD. It's called generalized Pareto because the case psi 0 is the exponential. And of course, psi negative, you're cut off from above. So it's a general, but it's basically, that's why the plus is here. But if psi is positive, this is just a slightly rescaled Pareto distribution. So this tells us, under very general conditions, and I'll come back to that, that these yellow peaks here above a high threshold, and I can challenge you, for every model you can write down, for every model F, for the moment for IID data, if I look at data, will fit somewhere in this theorem. And it's a big challenge. If I were to tell you, just find a theorem that does a distribution that does not fit here, a continuous, That's a very challenging question. We can answer it. But basically all standard distributional models fit there. And this was also a question earlier this week. So it's a very well-known distribution, 2 parameters. I can have a scale, a location parameter also if I need it. But it's shape and scale. And this parameterization you saw also this week, this is important. This is a contiguous parameterization, and doing the right parameterization, statistical applications, finding orthogonal parameters is extremely important. And for instance, Valérie Chavez-Desmoulins, when she will do her work, you will see that parameterization is really crucial always. Okay, so but now there's a condition here. F belongs to the maximal domain of attraction of a generalized extreme value theory. I would now have to do a bit of extreme value theory. I'm not doing that. That goes back to the Fisher-Tippett, but I will translate this result. So this is take home 3. There is a very clear theorem out there that if you're interested in, say, in continuous data, the distribution of peaks above high thresholds, then this is a canonical class. It's as canonical as the normal distribution, the Gaussian, the alpha stables are for sums. The mathematics is the same. For sums you have to go to the Fourier domain. For extremes you can stay in the real domain. The mathematics is identical. Different equation, but the thinking is the same. It all goes back to Khinchin. Well, for details you can go to some of these books we have written on also quantitative risk management, but there are all the details in there and all the software developed. Let me immediately go to an example to show that if I now push the button and I do the theory, there's a bit more hidden. And I did not mention the theorem. You saw the name, the face Ledbetter in the corner there. Indeed, it's not just that if I move up, of course if I move up I move out of the data, so there must be a scaling going on. That's exactly the scaling in the theorem, but there is more. This is look at the high U. This is the losses of my portfolio, the losses of whatever I study. So I'm now interested, can you say something about the limit behavior of the yellow process? Now what is the yellow process? If you look at that, this is random times where they exceed the level, and random heights, the excesses. That's a marked point process. In the theory of marked point processes, if my underlying data are IID or have, and I think there was also somewhere somebody mentioned that the D and the D prime conditions of Ledbetter, you can allow for non-stationarity, but you can allow for stationarity but non-IID properties. Then, under specific conditions, this rescaled process, the rescaling is going on here. U and N have to be nicely calibrated. Then this yellow process converges to a compound Poisson process. Now that's wonderful. Because compound Poisson in the limit somewhere, and you use that also, the compound Poisson has independence of the Poisson, homogeneous Poisson process and the sizes. I can, and Valérie will definitely do that, I can now decouple the likelihoods in a frequency part and in a size part. And of course then you go to the POC method and you can do like the smoothing you did and the non-homogeneous, and that's also what you will see in some nice examples of Valérie Chavez-Desmoulins. I just do a real data set. I do this quickly. I just say, what would this technology allow you to come up with? These are insurance data. These are fire insurance data, but I will not spend too much time on that. It's just a nice data set. It's a real data set. You can analyze in many ways. What you do now in practice, you gradually let your U go up and start a procedure for finding an optimal level U. That's the big Achilles heel. But you do the analysis, and once you've done it, it was mentioned this morning, you should not, was it that big lines and people plotting on log-log plots? Well, here's a log-log plot. I don't agree with the statement fully, but you have to be careful what you mean by this log. But you see this linear behavior, and this is the fitted GPD model. This is now the generalized Pareto. It really goes well in the tail. My U is 10 million in this case. The highest loss was 200 million. And now you see that this is a reasonable fit. I think this, by just eyeballing, this is a good fit. But of course, you will do in a proper analysis, and that's why I'm not entirely agree with the statement this morning. You do goodness of fit tests. There's a lot of statistical goodness of fit testing you can do on model and data. And now you say, okay, I want to estimate a 95% quantile. Okay, a 1 in 20 return period. So this, if you do that, your point estimate, so this is just a point, this is a log scale, you go to the fit, you go down 27 million. Okay, that's estimates, so I've seen the whole week already. Now I want to have confidence intervals, and now presumably you can't see them. No, you can't see them, I can see them. They're here. That seems very slight, you see this curve here. Well, you don't see it, I see it. There's this slightly parabolic curve there. That is the profile likelihood. There's a second one, so that and the profile likelihood where this cuts the model, the level here, 95% now, that's the confidence level now. There are 2 points I can read off, these are 23 and 33. Sorry you don't see it, but and I will not draw on the screen. I think I've done this once before, but it's... and then you say, okay, my point estimate is 27.3 million, but the 95% confidence interval is 23 to 33. It's asymmetric. That uses the profile likelihood, and this is take home 4. If you really want to do more modern extreme value theory and see what the weakness and the strengths are, you have to do this kind of standard methodology now. I put the second measure there, the expected loss given I have a high loss. I mean, this is what if. This is yes, the point estimate is about 60 million. And now if you do the profile likelihood, now I draw it here, I can just see it here on the blackboard. That's the profile likelihood. I cannot explain what the profile likelihood is. It's a standard methodology in statistics, in likelihood statistics. If you now drop down, you see it's 40 to 150 roughly. That's modern extreme value theory. It's not just giving you point estimates on checking your models, it's giving your confidence intervals. And I'm not terribly far in the tail. And I think extreme value theory, you can attack it, you can make statements like for the central limit theorem. At least it warns you on the width of confidence intervals, let's say here, 40 to 155, around your point estimates. And I would wish, I think, that more applications would really duly produce, in summary statements, point estimates. The question is, there was a condition in this theorem. Well, this condition is the maximal domain of attraction. Here it is concretely. This is Gnedenko. I said I will come back to Gnedenko. Well, this is Gnedenko's theorem. So now say this methodology I just showed you for the Pareto type distributions, power tail distributions, holds if and only if my underlying data, which I assume IID for the moment, I said I can have stationarity and I can adapt to non-stationarity, is indeed power tail, but with a slowly varying function L. Now the slowly varying function L is a function, a measurable function, that has the property that LTX over LX goes to 1 if x goes to infinity for all t. That is crucial. That's pure mathematics now. The whole mathematical approximation, also underlying Ledbetter, holds if and only if I have underlying data that satisfies this precise mathematical definition. It's power tail-like with the power tail you're trying to get at, but you can wiggle around it by a slowly varying function. This can be log functions, for instance. And this is making life difficult. So now I will cut this short, because I want you to take home 5, one extra name to take home. This is the name of Jovan Karamata, a Serbian a mathematician who really worked out the theory of regular variation. This is in the book by Bingham Goldie-Teugels. And he worked out this theory of these functions L. You can say, well, how can one really write now, in modern times, a whole book about these functions? Well, here is a meta-theorem. I can challenge you, find me a weak convergence limit theorem. Not just weak convergence, but basically a limit theory in probability, where the L function is not either explicitly or implicitly there. It's absolutely crucial. And that's indeed also why in Gnedenko's theorem, this condition, and this L will ruin your life. Because that is a non-parametric part of your underlying condition. You don't know it. You already have a big problem getting this psi out. All right? And that's a big problem. And I think one should be aware. I just will show you the consequence of that. The various, well, the first theorem I want you to remember. There's a very powerful theorem, and all the rest follows from that. You see here, I only ask pointwise convergence. It's just a measurable function, positive, 0 infinity, 0 infinity. It pointwise converges to 1. Well, it converges uniformly in all compact subsets of 0 infinity. And believe me, that's not an exercise. You read some really deep theorems from real analysis to prove that. But you get that. And once you've got uniform convergence, you can integrate limits and integrals, and you can the rest follows. You have Karamata's Tauberian theorem, etc., etc. So you have a whole series of powerful results. Now here's a warning. Why L matters. Again, go back to Pickens, Balcom, de Haan. I said that these yellow peaks here, in a precise way, after rescaling, converge to the generalized Pareto. And this is this distance du, that goes to 0. That's what happens for using the GPD approximation. And this holds even only if we have this condition a la Gnedenko. That's a condition. And now, I think a friend of mine, Sid Resnick, once wrote how the slowly varying function can ruin the risk modeler's life. And here it is. Because the big difference between the central limit theory and extreme value theory, although the mathematics is identical, is the convergence to types theorem. It's all the same. In the central limit theorem, you have fairly uniform convergence, speed of convergence. In the normal limit theorem, 1 over square root of n convergence. Whatever the underlying distribution is. Not true in EVT. In EVT, I will now look at here a little table here. It depends very much on the model. And let me just go 2 or 3 examples. You see, if my data are student or normal, the convergence is 1 over u square. This is a power law, depending on the degrees of freedom. This is just a standard normal. I look at the right tail. The log normal is 1 over log u. That's pretty slow. The log gamma, which is a power law, is 1 over log u. Now why? I can now put the parameters that this has the same asymptotic tail behavior of the student. Both power laws. And yet in the one I have convergence 1 over u square. In the other I have convergence 1 over log u. It's the L. In this one here, the L is asymptotically constant. Here the L is not. And I have the G and H, I will not mention it. But this is an example, you can stare at it from John Tukey in nice applications across various fields. It's a log normal and a log chi-square. It has a horrible slowly varying function. And it's the slowest rate of convergence I've personally seen in any real model out there. 1 over the square root of log u. That's the L function. This creates problems, always. And this is even at the more mathematical level. I'm going to a close now. I will not discuss this example. Let me end with a warning. You all know the situation of L'Aquila. Now, why do you think I mentioned this here in Cambridge? You see, there's the L'Aquila earthquake in April 6, 2009, and this is David Spiegelhalter. Why do you think I have this combination here? Yep.
Because he's very interested in public communication of risk.
Absolutely. Well, here's the Winton chair just down the hall here. He's in Cambridge. Here's the Winton chair for public communication of risk. It's all about communication. And if you really have been, and of course our friends in the climatological world, they're very well aware how difficult it is to communicate extremes to the press, to your colleagues, to whoever. And I think this is an area where we really have to do much better. And I think that's what, and of course this was a terrible case. Well, terrible, I cannot summarize it in one word. There are many sides to that particular coin on L'Aquila and the conviction by the Italian courts. I think it's still in rediscussion, but it was an example. Oh, sorry, yeah. Oh, here, okay, in L'Aquila, of course, it was badly, it was the communication was a problem. So the people from the expert committee. Oh, sorry, David Spiegelhalter, he's a professor, he holds the Winton chair in the public communication of risk. So he has a whole study program here in Cambridge on how do you communicate rare events, risks. And so I think if somebody like David Spiegelhalter would have been involved with the committee, I think in really thinking how, because this was the whole point, and I think you read perhaps the reports. If you discuss with the people there in L'Aquila, how they communicated the day before or 2 days before the event, what's the chance of and so it's I think that's the link. Okay, so we should think much more carefully how to communicate rare events. Of course, the same is true in even more, well, not more, also in environmental. So let me come to a close. I will not show you Holland without dikes and Holland with dikes, but that's, I think, one of the key applications of extreme value theory as a building stone. By the way, that's how it is today. You would be swimming around Amsterdam, I think, if the dikes were not there. And I come to a close. So there are many, many open issues still around. I mean, extremes for discrete data. If you say I want to do extreme value theory for Poisson counts, you have to speak to a specialist. The standard theory does not apply. You have to adopt it. There's no canonical theory in multivariate application because, of course, we don't have the standard ordering. So we have to say, what is large for you? Is large being you cross a hyperplane, in which direction? And then you get to the book of me and Balkema, and there you see the geometry coming in. Or is it a curved boundary in more dimensions? It's not like in one dimension, it's properly ordered, small and large. So you have to say what you mean by large. There's interesting links we saw this week already with rare event simulation, large deviations, and important sampling. We also saw the splitting techniques. So that's clear that extreme value theory plays a role there. High dimensionality, the statistics very rarely goes beyond 3 and 4. That's why the SIG is here. It's just very complicated, statistics. Time dependence, non-stationarity, and I think that's what your talk came into being, and I think later in the afternoon we have a talk by Valérie Chavez de Moulin, where you see how this methodology, especially this Ledbetter theorem, can be used for statistical estimation. Extremal dependence, I will not discuss it, but some of you may have heard the word copula. That belongs to this particular world. Nonlinear dependence, and of course communication applications. But by that I think I've really exhausted my time, so I thank you.
Questions, comments? On something, I would like to hear something about spatially distributed extremes.
Yeah.
I think, I mean, many work with time series, and
Yeah.
for example, get interested in if I have a random field with certain correlations. What should one expect for extremes or averaging of extremes? Because
okay, I personally have not worked on that, but I know there's a lot of work on modeling spatial extremes. I mean, you still have the GPD type distribution. Of course, now it depends very much how you model the interdependence.
Yes,
So it's I can just say there are various applications. There are various texts, also smoothing. It's a whole theory in its own. There is a lot of work there. I mean, I cannot summarize it in 2 or 3 sentences, but it's a well-established field. It can go to you can think of, the Earth is a sphere. Well, let's say in first approximation it's a sphere. So if we really want to model, let's say, global temperature, we have to model extremes on a sphere. And so there immediately get this kind of problem. So you have to have extremes on manifolds. So it's a huge field. And Robert Adler, he goes to the more geometric applications. I mean, also in brain imaging, and you get that sort of course, typically in grids, I think it's close to the standard theory, but it's a whole field on its own.
Yeah, I mean, you're bringing out yet another difficulty with, at least empirically, trying to check for power laws, because already you have most of the theories that predict a power law Taylor probability distribution don't tell you when the power law should start, and
that's the U. That's the U.
Yeah. So, but that's I know you're talking about this extra in the L, but it's already bad enough without the L.
I know.
Because all these Hill estimators, all these things, you have to already tell it when does it start.
That's the whole point. Why I mean, when I introduced this field in the world of finance, this was in the mid-90s. I was getting telephone calls exactly on that topic, not on the L, because I had no clue about the L, but on the U. I said, can you please give me an automatic procedure for setting the U? And this was, I think, was JP Morgan or Morgan Stanley. I said, no. I said, there are people that claim they solved it. No, they solved it under very precise second-order conditions on the L. It's not. I can only give you, in certain field of applications, my appreciation, perhaps 10%, like in work of Valérie, or somebody mentioned also the 100, 300 in the block maxima. in certain areas I can say, okay, that's not a bad choice. Of course, in the end, my confidence intervals will reflect that I've got very little data. But there is no solution. And that's also why I say it's ridiculous to set limits, especially in the financial world, let's say a 1 in 1,000 year event, a 1 in 100 year, whatever the interpretation. I always say, no, go lower. Why not go to 1 in 20 event? There perhaps you can do a reasonable estimate and then scale it up by whatever factors. You can have a fudge factor, an engineering factor, but don't try to put wrong signs into, well, no, it has to be like that. And so the real applications go for that, I think. And that's my experience when I discuss with people in practice. So there's no absolutely right, the U is, and you saw is the rate of convergence in extremes can be very slow. You don't really know in what regime you are. So it's a major point. On the other hand, these models, these GPDs, of course, they're following from a scaling principle. It's a scaling that if you go across higher and higher thresholds, these shape parameters stay the same. And that allows you to go deeper in the data and scale out again. It's somehow a belief that this scaling phenomena is around. And that's why I like this week, because people are trying to explain where scaling may come from. I'm a statistician, I just use that knowledge. Not a complete answer, but it's. I completely appreciate your comment.
Yes. I will give you some more examples later.
Thank you.
The independence, is it now broken?
Oh yeah, of course. It's like the central limit theorem. Of course, you know.
For practical question.
No, of course. We already know that we can do the whole theory for stationary processes under the so-called D and D prime conditions. When data don't have too much clustering and somehow weak dependence, kind of mixing, the theory still applies. We have done a lot of work where we say, okay, we do now regime switches. Because some people, especially in sociological applications, say, well, extremes only happen when regime switches. Then you have to start modeling that. So I entirely agree. So falsely believing that it's IID or close, I think is a big danger. You should model, and we will see examples later, we should model non-stationarity. I entirely agree. But of course you can still model stationarity and then do extreme value theory on residuals. So it's somewhere it comes in again. But you're absolutely right. But then you have to understand the underlying physics or economics.
Thank you for this beautiful talk.
Thank you.